the organizers for organizing such a great meeting. So let me start by telling you that I'm going to talk about some recent results related to the one electric dipole forbidden transition which we just found at our laboratory. It's going to be a joint presentation, so part of it is going to be by me, and the second half is going to be by Fernando. So, in general, the aim of our cold atoms laboratory is to develop the tools to control the internal degrees of freedom of atoms, and we have two research projects. One is to study the transfer of orbital angular momentum from structured light and atoms. That is, we want to study the modification of transition probabilities of electric dipole forbidden transitions, let's say something like this, a 5p to 6p transition in rubidium. And then we will talk a little bit about, at the end, about production of Rydberg states using external cavity diode lasers and also using efficient cascade fluorescence detection, for instance, in this sequence. So the outline of this talk is going to be, first we are going to talk about the electric forbidden transition, electric dipole forbidden transition, and then as time, if there is time, about Rydberg atoms, and then some conclusions, okay? So let me begin with an illustration of the electric dipole approximation. In the interaction between an atom and light, we generally assume that the wavelength of light is much larger than the size of the atom, so we have the atom like this quark in this wave. So there are no moving parts in the atom, say. Essentially, it just goes up and down, and that allows us to change this cosine of k dot r minus omega t to replace it with cosine of omega t in the Hamiltonian that describes this interaction, because the term k dot r is certainly much smaller than 1. Okay, now if we then compare the standard electric dipole transition, we used the standard electric dipole operator. That's an odd operator that connects states with opposite parities. And this leads to selection rules that are very well established. And the best example we have, say, is an S2P transition that is really, really fast. It occurs in about 10 to minus 8, 10 to minus 9 seconds, or 10 to the 7 transitions per second. Or if we compare this with an electric quadrupole transition, the operator is a quadratic operator in R. It's an even operator then, and so it connects states with the same parity. It leads to different selection rules, and the example that we are going to give is a P2P transition that is much, much slower, about a million times slower than the traditional S2P transition, say, in rubidium. So, the system that we chose is rubidium. This is the example for rubidium-85, one of the isotopes. And these are the levels involved in our experiment. So we have to first produce some atoms in the 5p 3/2 state. For that we use the standard D2 transition. And then we, with an infrared laser at 911 nanometers, we produce the excitation, the non-dipole excitation, into the 6p 3/2 state. If we change the wavelength to 917.5 nanometers, we can reach the 6p 1/2, that is slightly lower than here. And we detect this production of this electric dipole forbidden transition by the emission of this blue light that results from the spontaneous decay of the 6p 3/2 state. The experimental setup, we have two external cavity diode lasers, home-built. We built both. This is the one that produces the preparation transition at 780 nanometers. It is locked. to one of the transitions. We do this in thermal rubidium atoms at room temperature. The second laser produces the 911 nanometer transition, and then we cross them in counter-propagating configuration in a rubidium cell, and we detect at 90 degrees the blue light. We use phase-sensitive detection, and then we record all the data in a computer. So we also have a model. We had to propose a model because we couldn't understand what was going on. And essentially what we are doing is three steps, in the sense that the preparation laser is so strong and the transition is so strong that essentially the electric quadrupole only probes what this transition does to the atoms, in a sense that we have to include hyperfine and magnetic pumping effects here that are clearly, I mean, there is one cyclic transition and the others essentially pump the atoms out of the hyperfine levels, so we end up seeing only transitions, or the spectra are dominated by transitions from the highest hyperfine state in the 5p3 state. So we expect to see all transitions from this one, all the electric quadrupole transitions going up to the 6p state. So the electric quadrupole transition is weak, it only probes the result of this pumping here, and it depends strongly on the polarization configuration of these two lasers. And then at the end, the decay is described by the simple electric dipole decay of the 6p into the 5s by emission of 420 nanometers. By the way, this is almost completely isotropic, at least for these configurations. So in order to test this, we did a rate equation calculation of the populations, and this is the result, say, of this hyperfine pumping for linear polarization, say. It tends to accumulate all this, or most of the atoms, excited atoms, into the MF equals 0 magnetic state. And for circular polarization, we have an almost complete pumping into the highest M state in about 4 microseconds for our operation intensities. The dependence on the polarization can be explained here. We have this transition matrix element, and if we choose then, say, linear polarization for the preparation laser, and we set the z-axis along this, the electric field vector, and then we allow the linear polarization of the electric quadrupole producing laser, then we can say that, I mean, there is a very strong dependence on the relative direction of this vector with respect to this one. In particular, if these two are parallel, we probe essentially transitions that have a very specific delta MF transition probability, in the sense that we can only change in one the M projection. If we do perpendicular polarizations, if this angle is 90 degrees, we only probe the +2 or -2 transitions. If we change to a circularly polarized preparation laser, essentially we end up with this delta M equals to ±1 transition selection rules. Okay, so these are examples of the spectra. As expected, they are dominated by transitions from the highest hyperfine state of the 5p manifold, and the lines are where we expect, and the bars are the result of the calculation of using the rate equation approximation for perpendicular polarizations and for parallel polarizations. And you see that there is a very strong change in the spectrum. And so these ones are probing the delta MF equals to ±2 selection rules, these two on top for the two isotopes. And these two in the bottom select essentially are due to these selection rules, delta MF equals to plus or minus 1. Okay, we do the measurements a function of the angle, and they follow essentially a cosine square distribution. Again, it's an electric variable transition, but it follows a cosine square distribution. And so the three hyperfine components essentially follow. This is a single fitting result in the sense that we only fit the overall intensity of the three lines. We also did the other the 5p 3/2 to 6p 1/2 transition. There are only two hyperfine states in the upper state. Essentially, again, we follow the same the cosine square angular distribution, and we do see a very different intensity if we choose a perpendicular configuration as opposed to parallel polarization configuration. And so we think that our atoms are essentially doing that. That's the that's the charge density as a function of time, and that follows these different selection rules for perpendicular and parallel polarizations. And so Fernando is next.
Okay. So, so far what Pepe has showed us was our investigation of the dependence of these transitions with the states of polarization of the exciting light components. But the other natural thing to investigate and to establish well in our experiment is what's the dependency of these spectra with the power, with the intensity of the excitation beams. With the forbidden transition, we didn't manage to go that far in that direction because for producing the forbidden transition, we already had to put a lot of power there to see something. So we quickly ran out of power, and then we couldn't find any dependency really on the shape of the transitions beyond just the size of the lines. But the strong coupling that is given by the 780 nanometers laser or the deep line, that shows a strong dependency with the power. And here what we see is that dependency. What we clearly measure here is what it's called the dressing of the atomic states. It's an effect of the Stark AC effect on the atoms, how the spectral lines of this electron are responding to the strength of the magnetic field that is pumping. And what we found here is that by this model of 3 steps, by pumping with this atom and generating this strong coupling here, the second, the forbidden transition, works as an extraordinarily good probe for the system in such a way that it's not modifying the dynamics down here. So it's just a very quiet sample for measuring this dressing of the atoms without really modifying the dynamics here. So here I show you a little picture of how this develops. Each one of these lines is one particular hyperfine transition, and what we see is that as we increase the intensity of the pump power, we see that this transition is split in 2 components. So that's not extremely new, but we went further and we investigated this with more detail. And with the help of Dr. José I, that developed a very precise calculation of this, we first began with a model of only the 3-level system. This 3-level system that I showed here. And with that, and introducing the movement of the atoms in the thermal vapor, the Doppler shifts in the transitions, She developed this model in which we can see that it's not exactly the same as with what we are seeing. In particular, the central peak increases up to the maximum, and then it splits. And in reality, what we see is that it doesn't increase that much at the beginning, then it splits, and the two peaks keep growing. And we realized there that these decays that Pepe was showing in the full set of levels introduces some decays and much more richness to the physical system. So what Rocío did was to introduce a fourth effective level, modeling all these different decays and all this richness, gathering all that physical information in that effective level, and also introducing the Doppler shifts introduced by the movement of the atoms in the thermal vapor, and then we can see that we end up seeing that behavior, that the central peak doesn't grow that much, and then when the splitting appears, the two peaks keep growing still. So this gives us more a better understanding of what is happening in this excitation process. One interesting thing here is that we are not fitting any parameters here. We are just giving the real physical parameters to Rocío for plugging these values in the model, and the overall behavior works out pretty well. We think that we understand what it's measuring there. And this also, we know that by measuring this, the separation of these outward-downs peaks, of these doublets that appear in the center here, we have a way of measuring the Rabi frequency, the real Rabi frequency of the first step of the transition. So this is the work that we have been doing with forbidden transitions, and we didn't talk much about the motivations for this work. What we want to do with this forbidden transition was not to measure the forbidden transition by itself, but having a tool for studying the transference of orbital angular momentum between the light and the atoms. This is also a work from Rocío that she proposed that a method for identifying this transference of orbital angular momentum between these two states, between the light and the atoms, we could use, we need to use a transition that is beyond the electric dipole approximation, and that's the reason why we identified this transition and we developed all this spectroscopy system. And now we are already building a system for generating Bessel beams carrying orbital angular momentum, and the next step is to use this spectroscopy system to set it to work with the structured light beams and try to detect differences in these transition strengths between doing it with a Gaussian beam and doing it with a Bessel beam, and a Bessel beam with different orders of orbital angular momentum. We are also building this same setup in a cold atom system in a magneto-optical trap. Why? Just because by having the atoms in a magneto-optical trap, we have better control of the movement degrees of freedom of the atoms, so we can investigate this with more detail. And then the next stage would be to use this transference of orbital momentum to control the internal and movement degrees of freedom of the atoms, which goes into the direction of generating new ways of technologies with quantum systems. Also in the direction of quantum system, of quantum technologies, the other project that we have in the laboratory that we have been building there is the generation of Rydberg states in the atoms. So there what we want to do is to generate these highly excited states, mainly because the higher the excitation in the atoms, the longer the lifetimes, and then you can store information in those atoms with this interaction with the light for a longer time. And also, the further away the electron that we are exciting in the atom is from the nucleus of the atom, the stronger the interaction with other atoms around, and then it becomes a good physical tool for implementing quantum interactions within the atoms, and then calculations and all of those things. So that's the reason we want to build this, and we built this experiment in which we are using a 420 nanometers external cavity diode laser. This is a commercial laser, and then we built our own 1050 nanometers laser to excite. It's not extremely highly excited state, but this is our first system in which we demonstrate a strongly excited Rydberg atom, and we want to use this system for begin our investigation of these highly excited states. Eduardo Gomez mentioned that here in our lab we have experience building these external cavity diode lasers. Well, this is one of the examples of the things that we have been able to do. We bought the diode and we built the whole system, and this laser is already working, as I'm going to show you. One of the things, the feature that we have found here is that we can pump with a 420 nanometers laser, and then the natural way to detect this excitation is just to see the absorption of this line. But we also found that from the 6p state, there is a chain of decays that takes the atoms back down to the 5p state, and from there they decay that back down to the ground state by the emission of 780 or 795 95 nanometers light, and that can be easily detected, is the usual. And this actually, this decay, this cascade decay is actually more probable than the decay back through the 420 nanometers. So we demonstrated this spectroscopy system in which we send this 420 nanometers light and we send it back through the cell, and we detect the 780 nanometers fluorescence. And with that, we have been able to measure, this is the shape, what we see in a simple measurement, just by sending one beam in one direction. We see this fluorescence, and these mountains here, they are, the width of these mountains are due because these experiments are being done in atoms at room temperature or heated to a certain temperature. So this is an effect, the Doppler effect, what you are seeing here. But when we put the two beams in counterpropagating configuration, what we see is an effect of saturation in the center of these transitions. And from there, we can measure the structure of the 6p state, the hyperfine structure of the 6p state, and we even see some velocity selection features in our spectrum. One of the little things, interesting things that we are investigating right now, this is a Einstein equation model, the population movement of, in the atoms, the line, but we see that there are some points in which they don't fit, and this we know it's due to polarization control of the two counterpropagating beams, and we are playing with that to explain these optical pumping effects that are happening here. This is an interesting feature. And the second stage of the excitation is to use a 1050 nanometers laser now sent into a counterpropagating configuration into the cell, and we can measure now the excitation to the 20s state. I'm not going to go all the detail. These are all the possible transitions that are happening because the atoms are moving in there, and because of Doppler shifts, we have components on all these transitions. And these are examples of the spectra that we can see either for rubidium 85 or rubidium 87. It's the other way around. And then we can see that this is the main transition that we measure, the maximum F transition. And then these other peaks are due to the selection of velocities in the system. And we understand this, and we can even measure this splitting of the 20s state here by looking at the selection velocity of this system. So with that, I would like to conclude just showing this is the advance that we have in our laboratory towards the development of quantum experiments and quantum technologies. And this is not a fully updated list, but what I want to show here is this. All this work is mainly done by undergraduate students. In Mexico, it's very hard to have a lot of PhD students, but we indeed have a lot of undergraduate students with a lot of courage and with a lot of drive to do all these things and eager to learn. And indeed, they learn a lot in doing these experiments, as much that some of our students have had, with these works, have managed to go and do the PhD abroad, even getting scholarships from the UK, for example. One of them, Francisco, he did all the forbidden transitions. He's right now in Durham with a scholarship from the UK. Santiago is in Lens. Another one, Oscar, is in Oxford. So they have been very successful going into the PhD, partially because they have learned a lot of the basic techniques that they need to go straight into the lab and have fun there. Okay, that's it.
There's time for one or two short questions, please.
So my question is for Fernando, because it's about the orbital angular momentum. Now, first I want to make sure I've understood. Are you going to put orbital angular momentum on the allowed transition or the forbidden transition?
On the forbidden transition.
The forbidden transition. Okay.
The allowed transition is just to prepare the population to go.
Great. So now, my question has to do with the effect of the orbital angular momentum. Now, we've already heard today, and people have done a lot of work on having orbital angular momentum of light affect the center of mass motion of the atoms. What you're proposing is something that I don't think anyone's ever observed, which is the effect of orbital angular momentum on the internal state of the atoms. And I've asked people about this, and now I'm asking you. And what I've gotten as results from asking people is, one group of people will say that the effect is going to be small by the ratio of the Bohr radius to the size of the mode, which is going to be on the order of the wavelength of light if you use a high numerical aperture, and typically bigger than that. And then, so that means the effect is going to be down by the same factor the quadrupole effects are down compared to electric dipole ones. That's one class of answer. The other class of answer is it's identically zero. So what I'm wondering is, what's your view on this, and how do you understand it?
Well, definitely is on the first side. We believe that, and that's what Rocio described to us, is that if you want.
Yeah, well, maybe it has been observed. Oh, I didn't know that. Ah, I didn't know that. Who did it? Okay. Okay.
Yeah, so that's...
Okay, well, thank you very much. I think we're going to move on with the schedule, but please approach the speaker.